Okay, here we go. Focus. Speed. I am speed. One winner. 42 losers. I eat losers for breakfast.
Hello everyone. Today we're going to be looking at this problem. So we have the man, the myth, the legend, Flash McQueen, who starts a race at rest, so 0 kilometers per hour, and 10 seconds in the race, he's at 100 kilometers per hour. Today we're going to be trying to find three things. First, his acceleration, so his change of speed in the 10 seconds. Then, using the data from A, we can find the distance traveled in these 10 seconds. And then lastly, we're going to be trying to find some predictions. The next thing we want to do here is convert all of these into meters per second. So we know the initial velocity stays 0 meters per second because 0 is 0, it will not change. And then here we know 1,000 meters equals a kilometer. And we know an hour equals 3,600 seconds. So the hours cancel out, the kilometers cancel out, these two zeros cancel out, and we're left with an answer of 1 over 3.6. So we want to times this number by 100, is like the speed in kilometers per hour, but we want to know the speed in meters per second. So we're going to times 1 over 3.6 with 100 to know the speed in meters per second. This gives us an answer of 27.7 repeating meters per second. Okay, then we're going to be wanting to plug what we know into the formula for acceleration, which is the change in velocity over the change of time. So we have the final velocity minus the initial velocity, which is 27.7. Minus 0 does not mean anything in this case. So we have 10 seconds as the time because it's the time it took to go from the initial velocity to the final velocity. Then we simply divide 27.7 by 10 and give a result of 2.7, repeating, meters per second squared. Squared because we know it is the acceleration. In other words, it is 2.7 meters per second per second. Okay, so now we want to find the distance. So we have this UAM equation with all the variables we need, such as the position, x stands for position, time, the acceleration, and the velocities and initial positions. So this equation is very complex, so we're going to start by simplifying it. Position. This here cancels out because it's the initial position, which in this case is 0, so there's no point in saying plus 0, plus the velocity times the time, plus half of the acceleration times the time squared. We know that our initial velocity still is 0, so it's basically like saying 0 times the time. Whatever the time is going to give 0, so we can cancel this out again. And we're left with just this. Position equals half of acceleration times the time squared. So now, just like the last one, we plug in what we know into these equations. So we were left with position equals 1/2 of the acceleration, which is 2.7 times the time. So the time is 10 seconds, but there's a squared here, so it's basically just 100.
This is now the final and simplified equation.
When you multiply all these three, we get a final answer of 135 meters. So now here we have the distance traveled by Flash McQueen in the first 10 seconds of his race.
Lastly, we're going to be looking at some predictions for the future. So we have here a velocity versus time graph, and on the right, a position versus time graph. The x represents the limit to the data we have, which were the recorded 10 seconds, and the red line represents the trend line. This is very helpful to finding data that we don't know, so basically just predictions. For example, if we wanted to know what Flash McQueen speed would be 13 seconds after the start of the race. We would go up to this point in the line and then find its equivalent in the velocity axis. I calculated this using the same method shown previously in this video, and it gives us 35.1 meters per second. Same for the position versus time graph. You see here it's increasing exponentially. It's accelerating, so the distance increases every second. And then so same, if we wanted to find the position, basically the distance away from the initial position, 13 seconds after the start of the race, we would do the exact same thing, like this, match it with the position axis, and it would give us an answer of 228.2 meters. Let's zoom in on this. And then we know that every car has a limit and its speed cannot increase forever, which means it will not increase exponentially in real life. It will do something like this because the car would have reached its maximum velocity. In other words, terminal velocity. Since the car cannot go any faster, and it would not plateau because it doesn't stop, but it would continue like this. But in this case, it's very different. We're talking about Flash McQueen here. The man, the myth, the legend. He breaks the limits himself. This would not apply to the legend. His speed would continue increasing and literally touch the moon, the sky, the sun, break out of the solar system. He breaks the limit themselves.